Let me show you how to be a good Bayesian.
Today, we are going deep into one of the hardest problems in modern machine learning: how to scale Bayesian neural networks to truly high-dimensional settings without giving up uncertainty or computational sanity. My guests are David Rügamer, who leads a research group at LMU Munich working on uncertainty quantification and deep learning, together with Emanuel Sommer and Jakob, Robnik, two PhD researchers at the core of this work. In this conversation, we unpack why Bayesian neural networks still matter in a deep learning-dominated world, what uncertainty quantification really buys you in practice, and where standard approaches break down in high dimensions. We also talk about applications, community-driven tooling, and the long-term future of Bayesian deep learning, where it already outperforms standard neural networks, what's still missing for broader adoption, and why there is real optimism that scalable Bayesian methods are finally within reach. This is Learning Bayesian Statistics, episode 150, recorded November 20, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com.
Hello, my dear Bayesians. Before today's episode, I wanted to let you know that this year we'll be talking about Bayesian modeling in soccer at the Field of Play conference in Manchester, UK on March 27, 2026. So if you want to meet me, you can come there in the audience if you want, but also as a speaker, because we have already locked in most of the speakers and announcement coming soon. Stay tuned and follow on LinkedIn. Last year, we had speakers from baseball, cycling, education, fantasy sports, soccer, obviously, because it's Manchester. And that mix honestly genuinely raised the level of conversation. The theme for this year, 2026, is communicating complex ideas. How do you take something technical, nuanced, uncertain, like models, probabilities, trade-offs, and make it understandable and useful for people who are not data experts? Like last year, we are opening up one of the final speaker slots. So if this theme resonates with you or someone you know, whether they work in football or somewhere completely different, feel free to contact me and I will take a look. And in any case, you can already buy your tickets. Go to Field of Play's website or LinkedIn page and you'll have all the information there. I'm really looking forward to seeing you there, and I will for sure have some LBS merch with you. So please come say hello and come to my talk also, so that then I can say that the room was full, because otherwise I don't know what I will do. Thank you so much, people. I will see you there. And now let's go on with the episode. David Rügamer, Emanuel Sommer, and Jakob, Robnik, welcome to Learning Bayesian Statistics.
Thanks.
No, you bet. Thanks for taking the time, Emanuel and David. It's late for you in the evening, so I definitely appreciate it. And actually, I was recommended. I mean, you were recommended to me by a listener. Of course, I'm forgetting his name right now, but it will come back to me during the recording. So we'll get back to that, and I will thank you properly at that time. But in the meantime, let's start with you guys. Like as usual, we're gonna dive into what you're doing because you're doing really some fascinating stuff, the three of you. But first, your origin story. Okay, what are you doing nowadays? How did you end up working on that? And also, lastly, listeners, please forgive me for the weird voice. I am a bit sick today, but I have a dream team today to record with, so I could not cancel on them. So, David, let's start with you. What's your origin story? What are you doing nowadays? How did you end up doing that?
Yeah. First of all, thanks for having us. So I think Raphael was the one that brought up the connection. And yeah, what I'm doing nowadays, I'm a professor at the statistics department of LMU Munich. There I run a lab called the Munich Uncertainty Quantification AI Lab, short Munich.ai. I do teaching at the department, so I'm teaching statistics courses now and then, but my main duty is to teach deep learning, all sorts of deep learning, applied deep learning, the foundations of deep learning. Yeah, I'm also like a principal investigator in the Munich Center for Machine Learning, which is I'm very grateful for because they give you so much like network funding, etc. So it's actually one of the 6 big AI centers in Germany, and being part of this is pretty amazing. And yeah, how did I end up working on that? I did my PhD in statistics actually, and during my PhD, I already found these ML algorithms quite intriguing and quantifying their uncertainty. And that's actually something that then stick. And then, yeah, at some point I started working on deep learning, and nowadays, that's my main focus.
Okay, I heard it's a pretty popular focus lately for some reason. I don't know why. Emanuel, what about you?
Yeah, so well, my background actually is in math. So also in Munich from TUM, however. Now I switched sites to LMU, to David's lab, where I currently do my PhD, and with a very strong focus on Bayesian neural networks, so uncertainty quantification, quite generic networks, with a particular focus again on sampling, which also brought up the connection with Jakob. And well, I did actually a wide variety of stuff. Like probabilistic forecasting in financial domains, learning to rank in the industry before. And well, the common theme always was kind of the fascination with probabilistic machine learning methods, I would say. So quantifying some kind of uncertainty, I guess. And however, also the time as a practitioner, in fact, taught me that I can actually motivate myself much better if I envision my work to be of practical value. So that's why I kind of try to fuse probabilistic rigor also with a little bit of practicality, I would say. And I think that's, I guess, quite defining of my work now.
Yeah, I would say the same from what I've seen from your work, preparing for this episode. But we'll dive into that in just a few seconds. First, Jakob, what about you?
I am actually a physicist by training, and I'm currently a PhD student at Berkeley. I generally work on different problems in statistics and physics and astronomy, basically whatever is data-driven. And I'm recently also been developing MCMC algorithms, and that's how we met at the conference with Emanuel and we started collaborating.
Okay. So you all met at a conference, and then boom, these happened. Awesome. Yeah, I love it. Nice origin story. Maybe one of you, can you just give us a big picture overview of your group's work? Actually, you guys are focused mostly on Bayesian neural networks. What are the overarching research themes? Who wants to tackle that?
I mean, I can at least say a couple of words of what my group is doing. So we're not only doing Bayesian neural networks, but also things related to optimization. But optimization, sparsity, and then uncertainty quantification are the two pillars in my group, and we try also to combine that. And the idea is usually that this somehow helps in understanding neural networks better. So not from an interpretable machine learning XAI point of view, but more like can we understand their learning dynamics? Can we understand what the optimal solutions of those is? And then also maybe most importantly, what is the distribution of the parameters of these models? And that's exactly where the Bayesian neural networks come into play, because you get the distribution of the parameters, and by that you can understand a lot, even beyond the applications that I think we might also talk about later. But by having the distribution of the parameters, you can sort of already maybe understand better what is going on in these models. And yeah, that's the big picture in the group is actually, well, as I said, one of the pillars is the Bayesian neural network, is the uncertainty quantification, and ideally at some point we will be able to, I don't know, get big transformers or big other neural networks to give us the uncertainty for any prediction task immediately without any overhead, any computational overhead time. And then so you can have in any AI application, you get the uncertainty essentially then right away.
Yeah, man. Of course, you're preaching to the choir here. That'd be absolutely fantastic. How does it work? So, like, yeah, what does it mean to make Bayesian neural networks fast? How did you start doing that, and what does it mean concretely?
Yeah, so I mean, I think Emanuel can maybe give more details about that, but I can maybe briefly mention that. So we when we started, there was actually a couple of choices, and we found that this is super slow. Everything's super slow, and then at some point we realized that JAX is notably faster, at least when you sample these Bayesian neural networks. And yeah, I don't know, like Emanuel can maybe give you a bit more details about that.
Yeah. Well, basically, we're still talking about, maybe we can talk about comparisons with other competitive methods or other approximations. But like focusing on the sampling point of view first. So I basically got the idea for JAX from David. I think before starting in his group, I've never touched it. I've heard of it, but never touched it. And it worked quite well, like a charm. But then in the first project, I actually went for NumPyro as kind of the sampling engine with these classical samplers implemented. And in fact, it was actually super frustrating for me because it was reasonably fast, but not very modular. And I couldn't really get my hands on the core algorithms. And also some quite small details were actually not configurable, which made a huge difference when you actually want to scale these things up. So basically what I did quite fast is switch to blackjacks. Then it was quite a painful refactor, but it was well worth it. It's much more modular, and I felt like it was really good. Again, shout out to Raphael, by the way. He mentioned blackjacks the first time to me. And because basically there are some tiny things that actually make a big difference if you want to scale this up, like memory management, like really boring stuff. For instance, you would not want to carry, let's say, 100 samples of ResNet 50 models in your memory, which blows up quite fast. But you actually want to be able to implement callbacks, let's say, to actually save sampling samples at each time point, which is very unusual for the classical Bayesian, I guess. But if you work with neural networks, this actually makes things much faster. So there are actually little tweaks that kind of make this faster. But of course, compilation with JAX and works perfectly on GPU, TPU, and so on. That's pretty nice. But that's only one major pillar, of course. Like software is important, but you also have to kind of challenge these classical methodological stances that are well established in classical Bayesian inference. For instance, for us, some big steps were a parallel first budget allocation. So actually parallelizing a lot of things, having rather short chains, putting a lot of emphasis on ensembles, using hybrid optimization techniques, like actually getting a lot of information from optimization using warm studs cleverly. I mean, these ideas are not entirely new, like Aki, who was also on the podcast with you at some point, I think wrote a paper in 2000 where he kind of sketched that roughly with warm studs. So it's not nothing super fancy, but you actually just have to put all of these things together, and finally you also have to have a powerful sampler, and that's where kind of Jakob comes into play. That also makes a big difference.
Yeah. Okay. Yeah. That's really fascinating. And thanks for doing my job, Emanuel, because yeah, actually, Jakob, I think it's a perfect segue for you, because if I understood correctly, you worked on something called Micro-Canonical Langevin sampler. I have no idea what that is, so you're gonna have to explain it to me. And why did it play a critical role in scaling these methods to very high dimensions?
Yeah, right. So there are actually two things here. One is that is the actual dynamics that the sampler moves according to, and the second is how you actually implement numerical integration. So the first thing that we introduced was, the standard sampler MCMC in this kind of settings is Hamiltonian Monte Carlo, where you have some Hamiltonian dynamics that makes your samples move very efficiently and make it less correlated, and it's the gold standard. So what we changed here was instead of Hamiltonian Monte Carlo, we call it Micro-Canonical Hamiltonian Monte Carlo, Langevin Monte Carlo, which is based on a slightly different type of dynamics. The key difference somehow is that its velocity of the chain is fixed throughout the sampling, and this makes it somewhat more stable. Where you have sharp transitions in the likelihood and so on, the velocity doesn't just blow up and it keeps constant. This what makes it more stable. It also acts somewhat more deterministically, and this is one thing, but it's not the main reason why MCLMC, our Micro-Canonical Langevin Monte Carlo, is so fast. The main reason is actually how you do integration, because for either for Hamiltonian Monte Carlo or for Micro-Canonical Monte Carlo, you have some dynamics, and these dynamics in principle are designed in such a way that you get correct samples. But in practice, then you have to actually numerically integrate these equations to get your samples, and this numerical integration gives you some error, and this translates to bias of your samples. And the way this is usually approached is that you treat numerical integration as a proposal in a Metropolis Hastings scheme. So this is a scheme where you do integration and then you accept or reject as a sample. And this accept-reject probability can be determined in such a way that you remove the bias. And this is what people typically do. And it's a great idea, but it has a problem in high dimensions that you need to have an increasingly smaller step size as you increase the dimensionality, to keep the acceptance probability high. And so this is our main innovation, that we actually do not do this Metropolis correction, but instead we have an alternative scheme that controls the bias to be small enough so that it's negligible compared to the other types of error. And this is what really allows you to keep a constant step size when you scale up.
Okay, and so having this constant step size is really what gives you the most important improvement on the sampling velocity?
Yes. So, step size determine how fast do you move. And if the step size is low, then you have big correlation in samples. Mm-hmm. But with this scheme, you can actually keep a constant step size, don't lose efficiency with higher number of parameters.
Okay, but how is that? So what's the difference with the step size from the Hamiltonian Monte Carlo then? Because if I understand correctly, this is doing the same thing. So why does this, in this case, make such a big impact on the neural network sampling?
So In principle, Hamiltonian Monte Carlo can use the same scheme. It just usually doesn't. But people usually complement it with the Metropolis test. So yeah, what we did was find a scheme that makes it possible, and it's also applicable to Hamiltonian Monte Carlo.
Okay. Super interesting. Emanuel, it looks like you wanted to add something.
This with a few errors that are quite prominent in Bayesian neural networks to kind of put it together. At least that's my view on the whole thing, because that's one of the major pillars, as Jakob just mentioned. And then to also put it back with the main key ingredients to actually make it fast and valid in the very high dimensional settings is also the Hamiltonian. For instance, this metropolization correction also requires full batch. So full epoch through your data loader, which is not feasible for large data sets, right, that you encounter in deep learning. So that's basically a no-brainer. Actually, there was a really good paper from 2021. Vincent was also involved, who was also here on the show, that show that actually this acceptance probability then in these very high dimensions goes to 0. So that's a very hard result in that sense. And so metropolization adjustment doesn't really work. We can control that with the sampler. But then if you think about the approximation error in the sampling of Bayesian neural networks, you also have the initialization error and the Monte Carlo error. And these two then tie together to these key ingredients that I mentioned before. Because if you then warm start with optimization, which is really good, because we have known recipes in the community, everyone knows how to, by now, at least, to train a ResNet or any type of neural network by now, almost. You got pre-trained models everywhere on Hugging Face and so on. So you can actually start with a very well-researched foundation. And this almost eliminates or greatly reduces your initialization error. Then you still have the discretization error, which we tackle with the above mentioned approach. And then we then also have the Monte Carlo error, which is basically just the error that occurs from not having an infinite compute budget. And that's where basically being smart about your budget allocation makes a huge difference, especially in these multimodal complex geometries, where we then use a lot of emphasis for our ensembling, and then we enrich this via very flexible local approximations. Basically what means we use rather short chains. So that kind of puts it all maybe in context.
Yeah. Okay. Yeah. Thanks, Emanuel. Very, very helpful. And so I think you guys kind of answered here and there that next question, but I'm curious if you can make like a summary maybe of how, like, what were the main bottlenecks that you encountered when doing the scaling work of Bayesian neural nets to high dimensional parameter spaces? In, well, the how you overcame them, we just talked about, but well, what was the main list of main frustration, I would say, that I'm guessing a lot of practitioners are encountering right now without your work?
I mean, I can try to answer, but I think Emanuel also and Jakob to some extent, or actually already answered it in some way or the other. So, I mean, first of all, I think the software was one of the bottlenecks that if you use PyTorch and then you do the sampling, then that even in very, very, very small neural networks was 10 times slower, maybe even slower than 10 times slower. And then this is kind of a bummer, because if you work with, I don't know, a single hidden layer 3 neural network, and you have to wait for a day to sample it, which is actually still the case so you can ask ChatGPT to write code for sampling a Bayesian neural network. And if it does that in Pyro, and you run it on, I don't know, Google Colab, then it will probably take quite some time, and you will maybe ask yourself whether this is actually working, or maybe if you want to give up. And there, I think it's very important to know the software to maybe switch to JAX. I think that you can still make it work with PyTorch, but then I think JAX can be faster. So why not use JAX? I think there's also a lot of other communities now potentially switching over to JAX. Maybe Emanuel can say something about this later. Once you have this hurdle, you manage this hurdle, the software hurdle, then I think there's a couple of other things that are challenging in Bayesian neural network sampling. The standard stochastic samplers don't work off the shelf. This is pretty difficult to tune them.
So you mean something like the nut sampler here, right? To be clear with listeners.
Well, the nut sampler, I think in most cases is, I guess, used with a full batch setting where you feed in the whole data set, but then there's stochastic samplers that only feed a small part of the data set into the like sample based on a smaller part of the data set. And then this will become quite unreliable, and also it requires hyperparameter tuning. So this is not something that at least there are not these defaults that are available maybe like for Adam or stuff like that where you can just run it off the shelf and it will work. And I think we put in some effort also into this. I mean, the one thing that Emanuel mentioned was this initialization thing, right? If you initialize already in a good region, then this is another can be another big bottleneck or big hurdle, because samplers are not necessarily good, at least from our perspective, to do the job that an optimizer does, to traverse some traverse the weight space and find a completely different topological space, like in terms of like weight distributions, completely different weight distributions. It can do that, I think, but then in practice, maybe step sizes play a crucial role and stuff like that. And so, at least in from our experience, it was way more efficient to, as Emanuel mentioned before, start your sampling from a very good starting point already, from a maybe optimized neural network already, and then you can also overcome this hurdle, that the bottleneck that the sampler needs to find, first of all, something. Needs to find the typical set where and to sample from that, and it has much easier time to do that, to find the typical set if you initialize it the right way.
Okay, so here very concretely, that would be you would feed your neural network in a classic way with the Adam optimizer from PyTorch, for instance, and then use that as the initialization of your Bayesian neural network sampling algorithm, if I understood correctly, not with nuts and with another package probably based on JAX. How wrong am I here?
No, you could also use nuts. You could use any sampler. I think they will all profit from the fact that you initialize these in the right region. But then, as Jakob said, MCLMC based samplers could be more efficient in high dimensions. I mean, nuts still works, so we did that, and you get similar performance in these Bayesian neural networks, at least in maybe not super large Bayesian neural networks, but practically relevant Bayesian neural networks. You get a similar performance with nuts than with as with MCLMC based sampling, but then it's slower. It's notably slower.
Okay. Yeah, so actually that was something I wanted to ask you later, but since we're on that, and maybe Emanuel, because I think David said you might have things to add to that. Like concretely, how can curious listeners try what you're talking about right now, like these methods that you've developed? Is there a reliable Python package they can install and play around with?
Yeah, so basically, if you want to check out MCLMC, then Jakob and his crew has done a tremendous effort to put that into blackjacks, which works really well, as I said before. But at the same time, maybe blackjacks is a little bit more for the tech-savvy guys, right? Because it's quite configurable. But what's actually quite nice about the whole JAX ecosystem is also that it has this functional character, right? And this actually serves the purpose of for instance, sampling a Bayesian neural network really well, because if you think about it, what you need for gradient based samplers like MCLMC or HMC is you just need to evaluate your likelihood, your neural network, get some gradient out of this. And this is the same thing that you need for optimizing your neural network. And if you just have a set of parameters, let's say you can imagine it as a dictionary, you can just handle this through the whole pipeline. You just use your classical optex, for instance, your optimizer, you just optimize your network, and then you do just take out basically in each step the same tree of parameters, and you just put it into the next step, whether it be an optimization step or a sampling step. So it basically kind of, you can play around with your parameters. You can even switch up things right in between, like for instance, cyclical SGLD would do. So you can actually be quite flexible. And I think this functional approach to sampling and optimization also teaches you that both of these approaches are kind of similar and also share a lot of things. So actually you can smooth out this hybrid approach can also be done in a very smooth way, like transitioning from a non-tempered or highly tempered, so basically optimization phase into a non-tempered sampling phase, for instance. So you have a lot of things to do, and I think like jacks and blackjacks are a good combo, and maybe also we will publish some code which is more user-friendly than our usual research code also soon. For PyTorch lovers, I would like to advert this Sam Duffield's Posterior package. So this comes with a lot of ready-to-use samplers, especially for the stochastic case, so they scale up quite well. And they also come with some variational or approximate Bayesian optimization-based methods. We also use these methods a lot for our comparisons because that's just a well maintained and easy to use package for Python. And well, soon also our group will probably release a hopefully very accessible, very user-friendly sklearn compatible package that is tailored to the tabular case, so for classification regression, and that implements basically this hybrid Bayesian deep ensemble approach together with an MCLMC based sampler. So that's maybe my 2 cents on that.
Yeah, this sounds really cool, really, really practical. I love that. We definitely need, as soon as you have these package available that you just talked about, send that to me, and I'll make sure to post that around in the LBS universe, because you have a lot of people here who I'm sure are waiting for that. And also, if you can already post the links to at least the Posterior's package from Sam that you talked about in the show notes for this episode, that'd be great, because it sounds like it's mainly the main way of interacting with these methods. Like the fastest and easiest way to interact with those methods would be there, and then I put the link to blackjacks already in the show notes. So if you listeners wanna dive into that, they already have blackjacks and posteriors. And once you guys have your package, and I'm guessing some notebook examples, we'll make sure to add that to the show notes a posteriori, but also to make sure that people know about that, because I think it's extremely helpful to distill the great work you guys do at the research level and just disseminate it at the practitioner level. So yeah, thank you for investing time in this. That's extremely important. Anyone want to add something on that before I ask another question?
I mean, I think we will certainly have a package also from our group. I think this is and also, I mean, we could already link to research code if those are for those who work in research. I think you're nowadays you need to work through the others group's research code, and I think we happily can provide that as well.
Well, maybe I
Yeah,
should
for
also
sure.
say that if you are not interested just in Bayesian neural networks, but in general statistics sampling, actually Blackjacks integrates pretty well with other standard probabilistic languages. I don't know, you can write your model in Pyro or whatever, and you just extract the
PyMC.
log likelihood from it. It's a one-line thing. And then you can plug it any sampler from Blackjacks, and there are also tutorials how to do that, so it's pretty straightforward.
Yeah. Like if you want something a bit less in the frontier of the Bayesian research, because Bayesian neural nets are pretty much at the frontier right now. If you want something a bit more classical, Blackjacks plugs and plays very well with Pyro and Pyro, and of course PyMC. And Bambi also, you can, if you're using Bambi, you can access it directly from there, which is great, especially for beginners. You can have Wilkinson notation models and then just use Blackjacks to have great samplers. That's amazing. Actually, a more generic question I had for you guys. Well, before that, actually, you were right, David. That's Raphael Rems, who recommended me to you guys. So thank you so much, Raphael, for being such a long-time listener, and also, being now you're a matchmaker, so official LBS matchmaker. Thank you so much. But yeah, like a bit broader question is, I'm curious, how do you guys think about the trade-off between computational efficiency and posterior fidelity when designing and choosing which algorithms to use for which model? Because something you need to do as a practitioner usually is you need to justify, like, people, when they know you use Bayesian models, they usually associate that with nuts or MCMC, right? And we know nuts and MCMC, they have these, they take longer to fit, but they have these guarantees of convergence in the long term, which you don't have necessarily with other approximation algorithms. People may be familiar with ADVI or DADV, which is something we talked about on the show with in episode, I think, 147. So I'll put that in the show notes. But yeah, or Laplace or INLA, things like that. But these come with more assumptions than nuts, but they are faster. So in this case, you have to be careful of your assumptions, make sure that the assumptions work and your prior predictive samples make sense most of the time, and that the model is able to recover the parameters from a prior predictive sampling analysis with fake data, let's say. How do you guys think about that in this case, like when you're doing Bayesian neural networks?
I can maybe add, or sorry, please.
I think I actually wanted to say that Emanuel probably can say a couple of things there, but then maybe just as a general note, I think the VI methods that are currently out there, they are not necessarily fast. I think you get a I would say in the same amount of time, potentially get better performance with sampling actually. But yeah, I mean, Emanuel is the expert there. He can probably say more about this.
So just wanted to say that maybe I will just give a perspective from the BNN case, and I think Jakob also knows a couple of other perspectives quite well. So he can maybe also give a slightly different perspective also from different areas where maybe also you actually go this way of thinking that you kind of outlined. I would like to kind of revert it completely to maybe start by the most crude approximation that you could think of. That is also often advertised by Andrew Gordon Wilson at his group at NYU. If you think about these Bayesian neural networks and the approximation of the posterior of these huge spaces, you can think first of the most simple thing. You have just an optimized model and you put a Dirac prior on exactly that model, and that's the most crude approximation that you can basically put onto that very complex posterior. Well, then you can basically step up an edge and you can actually include an explicit prior, you do map estimation, then you choose a restrictive family of distributions like a factorized Gaussian, then you approach basically the whole thing from a variational standpoint of, you can also basically put a Gaussian on top of your local approximation, which is then a Laplace approximation, which is already, as we have shown, as many research basically across the field have shown, aids generalizability, also performance and robustness in many cases, and calibration of the predictions and, for instance, credible intervals from these predictions. And then you also you can ensemble these things, right? And you have an ensemble, let's say, of Gaussians, of very high dimensional Gaussians. So you have a mixture of Gaussians, but still that's not quite flexible, right? So taking it from there, you can also, again, use an ensemble, but then you don't impose any, as you said, restrictive assumptions, but you actually do some sampling, which is very flexible, very efficient if you then use, for instance, very strong gradient-based samplers like MCLMC. And then you get much more flexible local approximations. And then you still, if you want to be correct, and also if you want to not just lie about things, obviously this is an approximation to this huge dimensional space. Like in the last weeks, also in a project where Jakob is involved, we sampled a vision transformer with, for instance, 22 million parameters. We sampled all of those, and we obviously did not collect millions of samples from this very, very large network, but we collected many thousands of samples, in fact, of this model. So, but still, in comparison with the dimensionality of the problem, this is likely a very crude approximation. But if you see the whole transition from this very crude Dirac delta to these restrictive local approximations to this then flexible local approximations, you can see that you have gone quite a long way with all this flexibility. And then if you then look at performance functionally on uncertainty quantification methods, even just predictive precision, you can actually see that this works. And this then is also not much more expensive than the optimization after all. And it's also, at least if you are, again, a little bit smart about how you do the whole thing, in my experience, also more robust compared to, let's say, variational approaches in these high dimensions, because these also come with a lot of hyperparameters, and they can also be quite brittle, like because of very noisy gradients and so on. So overall, I think that actually this Bayesian deep ensemble approach, while still being a crude approximation overall in the big picture, is a much more flexible and precise and quite beautiful approximation of the whole thing than, let's say, other very, very crude things. But of course you incur a lot of error still. So I think then from the other side of the very high fidelity posterior reconstruction, there you have to ask Jakob.
Yeah, for sure.
Yeah.
Thanks first, Emanuel, for this very practical rundown. I'm really looking forward to you guys' example notebooks. I think you should definitely write stuff here and basically make these. Like this stuff is in your papers, but we need that for practitioner. I think it's going to be super helpful, honestly. And so Jakob, yeah, what do you have to say about that?
Yeah, so I usually mostly think about, more scientific applications where you don't have a Bayesian neural network, but you are, literally trying to learn the posterior and you want it to be the exact posterior. So the MCLMC, if you include metropolis adjustments, has similar type of guarantees as the standard HMC samplers, which is to say, if you assume something about the target, like, it's log convex, something like that, then you can show that they actually converge. But as soon as the target is, has multiple modes or something like that, then you lose all of the guarantees in any case. So there are really no theoretical guarantees in either case, whether you include adjustment or no. So I'd say everything is about the same setting here. The critical part is how you make it work in practice and how you look at the diagnostics in practice after you run the chains. So, for example, standard, people look at things like Kerman-Rubin statistics and stuff like that. And we are actually right now also working on similar types of diagnostics also for our scheme without metropolis adjustment, where you can basically check that your bias is as small as you would like it to be. Yeah. So yeah, I think it's a very practical question, and yeah, it's an art.
Yeah. Yeah. I know. Sorry for asking these practical questions, but it's like, oh, that's what I do here.
I mean, no. I think it's an important question, definitely,
Mhm.
and
Yeah.
we are thinking a lot about it, and
Mhm.
yeah.
And actually, since we're on the practical side of things, I'm curious. How do your Bayesian neural network models compare to standard deep learning approaches? Both in predictive performance and uncertainty calibration. I think that one is going to be for you, David.
Yeah, I mean, of course, in our papers, not of course, but they usually perform better both in predictive performance and uncertainty quantification metrics. This is maybe sort of obvious because essentially we have a big model average over like every sample is a weight vector of is one neural network, and then we have a huge ensemble of these of all of these networks, and then I think this is also, I mean, that has been shown in the past to be very promising. Ensemble methods have worked for random forests, boosting, stuff like that, right? And they also work extremely well for Bayesian neural networks. Yeah, as Emanuel said before, the uncertainty quantification metrics, at least those that are currently used, these Bayesian neural networks also outperform the standard deep learning approaches by a large margin. Again, you could say this is obvious because you're comparing one neural network versus like kind of a big ensemble of neural networks. But well, you have to first come up with this ensemble, and that's the art then to sample from these Bayesian neural network posteriors. Yeah. Emanuel, do you want to add something, or?
I think that puts it very well. I mean, for some problems, we even sometimes cut metrics in half, right? Like an RMSE. For some problems, it's task specific in a way. It works for all different kinds of models. Like in our this year's iClear paper with Jakob as well, we also had applications to different data modalities like text, images, tabular data, all different kinds of models. We have now sampled the VITs, NanoGPT, you name it, resonance. It basically is a very generic way of formulating the problem. And then in the end, of course, you don't get a huge margin in each and every experiment. But I think what's quite encouraging is that you're never worse kind of than the standard deep ensemble, which is a really strong baseline. Like you can actually make it work to always give an improvement, and then it's up to the user whether this improvement is worth the extra effort, which we try to keep very low. And also that is kind of the choice of the user. Like how long would you sample from these very good starting points? And obviously if you in most cases, it saturates quite fast the performance, so you don't have to sample for an excessive amount. But obviously, you can just take a few samples, and which maybe a few samples more would give you slightly better performance, right? But then you basically have to trade off, as you said, computational efficiency versus your performance at inference, kind of. And also, like to also showcase maybe that it's not the same. It's not just compute, right? If you spend the same amount of compute for mean field variation and inference, for fitting a lot of, just optimize a lot of ensemble members for a deep ensemble, and spend the same amount of time for sampling, you can see that for this given budget, you can actually make sampling work much better, especially on these uncertainty quantification metrics. So there is some magic sauce to the sampling itself, because if you think about it also, obviously you also bias your model average which you have in the end. If you, for instance, have a deep ensemble, and if you just optimize each model, you don't have any kind of exploitation part in the whole thing. And other approaches have already experienced that as well. This like exploration exploitation trade-off. I think you had Ingen Lee on the podcast as well with cyclical SGLD, which kind of is the personification of exploration exploitation trade-off. So this again holds here as well.
Okay. Damn. And something I'm curious about actually is, I think, so the way I see the models we're talking about right now is mainly as an add-on when you're limited by the classic deep neural networks, right? Where you need actually the Bayesian machinery for some reason. So first, maybe you'll tell me, no, actually there is a need in itself for this, and I'm happy to hear about that. But also, what I'd like to hear from you is, in which cases would you recommend listeners to look into that? What kind of real world problems do you see as the best fit for these fast Bayesian neural network approaches?
I mean, I can briefly answer, and then maybe Emanuel or Jakob can add to this. So I think in general, because the computation, the overhead is not that large anymore, that big anymore. I would rather, I would actually ask whether it's not worth doing it for all the applications, because it's, as I said, like the overhead is not that large, and then you get a better performance, and you get uncertainty quantification. You could argue that this uncertainty quantification is not do I actually know the Monte Carlo error that I incur by not sampling 1 million samples, stuff like that. But then the metrics that we measure for uncertainty quantification are usually notably better than if you apply version inference or Laplace or something. So maybe you are not there yet. Maybe you don't get the uncertainty quantification that you would want to have for your Bayesian networks, because there's still a limited compute. But then you're doing better than everything else that is there. So I don't see any reason not to use it. And I mean, there has been so many there's no specific domains. I think, as Emanuel said, like you can apply it to all sorts of Bayesian neural networks. I think we're still not clear how effective it is, or how much it brings to the table if you apply this for generative models, right? So you could apply those also for generative models. You could sample, as Emanuel said, a nano GPT model, and then generate text from a nano GPT model. Does the additional uncertainty in the parameters, in the weights, does that somehow improve the generation? That's, I think, still unclear. But then again, for all the other supervised learning tasks, I think this is why should you not try it if it has not that much of overhead.
Yeah, no, 100%. Especially, and that's why I push always for these reproducible workflow accompanied with a reliable Python package, because then it's like the entry cost is super low for practitioners. And so it's like, well, you have the package here, you have the example notebook, just, try and sample it up, fire it up, and see what it gives you. Maybe it's still too slow for what you need, and that's fine. But maybe it's actually really what you need, because all the bells and whistles you get from the Bayesian approach are going to be extremely important for your use case. So yeah, like completely agree with that. Emanuel and Jakob, anything to add on that?
No, that's
okay.
Pretty well.
I think David did good job.
Yeah. Actually, I'm sure, probably Jakob, you'll have something to say about that. Do you have an example in mind, or maybe a theoretical use case from you knowing the theory so much, where a Bayesian neural network with the micro-canonical sampling approach could reveal something or revealed something that the classical neural net would have missed?
I mean, again, I think that, yeah, I don't think so. I mean, from the large language models, there's this mixture of experts hype right now, right? So there seems to be really something that you gain by mixing experts, by combining models, and I think I think you would profit in. I mean, there's certainly examples, and we saw that also in benchmarks. We saw benchmarks where, I mean, Emanuel was, I think, very open about this before. For certain combinations of data set and neural network architecture, there might not be an improvement in the predictive performance if you ensemble models, or there might not be a better uncertainty quantification than if you just put a Gaussian around your optimized value. But it's usually not worse than that. It's not worse than these comparison models. So yeah, I don't know. Like, well, I think maybe the thing that Jakob could have answered or could have said is maybe there are, I think, some non-Bayesian neural network applications where you can definitely show that MCLMC does notably better than other methods.
I mean, if that's what you mean, non-Bayesian applications, there is plenty where without MCLMC you cannot explore the posterior sufficiently. Your correlation length is just too high. For example, we're working on cosmology applications, and there a big thing is now field level inference, where you want to, together with your parameters, describe how the universe evolves. You want to also learn the entire field of the universe, and this is millions of parameters, and as the service gets bigger, it's getting bigger. So we're also getting in the machine learning dimensionality regime. Yes, definitely, if you just run nuts, you will basically not converge in reasonable time. So people have just given up on that and tried Laplace approximation and other this type of approximations. But if you run MCLMC, then you actually get a good posterior that's more reliable than approximations for sure, and it's actually even faster than the approximations. So yeah, in this type of applications, it's very important.
Okay, yeah, I see what you mean. And actually, do you think, Emanuel, anything you want to add on that, or is that fine? Okay, cool. And Jakob, and of course, David and Emanuel too, if you want to jump. But I'm curious if you do expect micro-canonical methods to become more widely used in Bayesian machine learning, or do you see them mostly particularly suited to the specific classes of models we've been discussing today?
No, they're actually very general purpose. We have been trying it across models, like various different models, from Bayesian neural networks to, as I said, physics applications to quantum problems. Basically, you name it, or benchmarks, and on none of the problems we found it to perform worse, but usually it performs much better, especially in high dimensions. It can be orders of magnitude faster. So yeah, it's definitely not a problem-specific application.
Okay, yeah, that's cool. That's great to hear. And actually, so that opens me up to two questions I have a bit more regarding the future, which is how optimistic are you guys about the feasibility of getting to where you were talking about at the very beginning, David, which is Bayesian deep learning at scale without latency, to put it in a very ambitious way, as a default in the future. How optimistic are you about that, and what breakthroughs do we need to get there?
So I would be very optimistic about that. I think that in a couple of years we probably are. I mean, it's still. I mean, we're not. So I'm optimistic that we can solve any, or that we can sample Bayesian neural networks of the size that now people in research, for example, optimize. Maybe not the company neural network sizes like OpenAI's GPT-5 model. I don't think will be able to sample that. That this is just not. I probably also don't want that. But other than that, I think there's almost no limit to there's a limit that for the typical use cases. So none of the researchers that I know outside of OpenAI or all the other companies that run these large language models, all the researchers that I know, they could I think in 2 or 3 years sample their models as well instead of just optimizing them. And then there might even be approaches that maybe researchers from OpenAI and other companies are using that instead of sampling to get something like a Bayesian neural network, like for example the I1 optimizer from people from the Recon group in Japan. There are still some open problems that maybe Emanuel can mention. But I'm very optimistic. So there was a paper in the past from Andrew Wilson's group, again, where they used a lot of TPUs and a lot of runtime to sample these Bayesian networks. And I think essentially what they did, we can do now in an hour or two with standard GPUs. And I think this will just get better and better. And then, as I said in the beginning, maybe at some point we actually have like a meta model that doesn't even that gives the sampling the samples right away without doing the actual sampling. That is a generative model that can generate probabilistic distributions right away. And we have shown that this already works for small applications, for small models. Like you can essentially replace an MCMC sampler with a transformer and gives you the identical posterior by learning a distribution in this transformer instead of sampling from it from the model's posterior. But yeah, sorry, I think Emanuel also had some comments about the scale thing.
Yeah, but thanks, David. That was super, already super interesting. And I love that future, at least on that part. So yeah, like I completely agree. Emanuel?
Yeah, I mean, to be honest, I totally agree with that future. There are still a couple of obstacles, but I think they're also manageable. I think one thing, for instance, would be basically, but that is shared for variation inference, Laplace, and so on, is that at inference time, you sample again, or you basically have to do forward passes through all your models that you saved, basically your samples. So this obviously incurs extra latency. And I've been to industry, and latency is relevant, right, for the end user, especially if you have user-facing applications. But I can tell that there are groups that are very talented. We are also maybe among of them that are working on basically distilling this knowledge down. And David mentioned a future where transformers can learn that, which is not too unrealistic by now, and also classical distillation or methods from statistics could be applied there. And I've even had some POCs on my laptop that didn't make it out to the public, where I've seen that you could speed up the inference cost by like a factor of 100 quite easily without losing any performance. So I guess there's a bright future ahead for these sampling methods, which are not classical sampling methods anymore. And I think that's actually something that people have to realize, that a lot of these classical things don't work anymore, especially for BNNs. Like we've also put this into one of our papers. The Gellman-Rubin statistics or the effective sample size was mentioned. They don't make any sense in non-identifiable models, for instance. So you actually have to switch gears a little bit, and you have to be smart about things. So, but with these, with also all this understanding that you can also get from, let's say, the optimization theory part, if you actually digest that, and then you can come up with quite simple recipes that are quite robust, that are often hybrid models between, let's say, optimization and sampling. And applying those is actually very feasible and pretty performative. So, I mean, I also think there's quite a bright future ahead, and there are actually, like, I can name 4 papers right now that sampled quite large networks, and they were published this year at AI Stats or iClear. So there's a lot of progress actually in this field.
Yeah, that's really incredible. Great time to be alive. Jakob, do you want to add anything on this topic?
No, I think guys already answered everything.
Okay. So actually, I'm curious also to hear you guys about. Okay, that's what you would like to see, and that's how you envision Bayesian deep learning at scale to look like. Even more concretely, I am also wondering, where do you see the interaction of the method, the concrete packages and methods we talked about, so JAX, blackjacks, and Bayesian inference? Where do you see these heading in the next few years, especially with these new samplers, these new methods we just talked about?
Probably best if Jakob or Emanuel answer this one.
Mm-hmm.
Maybe I can say 2 words and kind of kick it to you, Jakob. So basically, I think we're developing quite good code. I think there needs to be kind of a community effort to actually commit on a certain type of package, but the big flexibility, like Posterior is already a good step into the right direction. But I think like actually delivering a package for the whole pipeline, like, because Posterior's package is just the sampling. So in fact, to kind of put it together, it also does kind of the optimization part, but you need kind of, at least for these hybrid methods, you need like optimization, you need sampling, and then you also need to take care of the samples, as I said. Like you have to actually manage all these samples. And that's actually something that many people forget, because that's kind of this boring engineering that just goes into actually making these things work at scale. Like you actually have to do it also in at inference, you need to assess all of these samples. You have to do this in batches, you have to do this efficiently. But you can do that with JAX quite easily, but you just have to put out the engineering. But also what I've seen in the blog of, for instance, Andrew Gellman, which I think is quite encouraging, he also just recently mentioned Jakob by name and also blackjacks. And I think this also will spread a lot in the also classical Bayesian world. And I think, Jakob, you have a better view on that.
Yeah, it seems like a lot of Bayesianists are turning to JAX, and so blackjack's philosophy is to somehow provide a skeleton for samplers. It doesn't provide the end results. That's the philosophy. I don't think that will change. So the goal is not to provide one-line calls that you can do to the sampling, but to give you, as Emanuel already said, like the ability to tweak all of the little details if you want to. So I think that's a great start, and I like it how it's framed. But we also, of course, need to also put out the final results, as Emanuel is doing, and also in the more classical sampling world, I think that's maybe one missing piece, something to put together the different samplers and make them very user friendly.
Yeah. It's like, this is really a full stack work, right? Which is kind of the difficulty. You don't need only the technical implementation, which is already extremely hard in itself, but then you need also all the thing around it, all the communication that goes afterwards. How to make sure people know about your method. How do you explain to them without being overflowed by the customer support, let's say, and all that stuff that's beyond technical abilities was extremely important, because in the end, a great package that nobody uses is a shame. So that's also why I'm doing that, and making sure we shine the light as bright as possible on things that really can change the game for a lot of people. Fantastic, guys. That's really cool. I'm gonna start to wind us down here because it's late for you guys. But is there anything I didn't mention that you would like to mention here before I ask you the last two questions? Cool. That means I did a good job, because I had a lot of questions for you guys. So I'm very happy about that. Again, like to all the listeners, check out the show notes, because they are quite big for this episode, and I think you'll really, really appreciate them. There's a lot of really cool nuggets in there. But as usual, guys, before letting you go, I'm going to ask you the last two questions. I ask every guest at the end of the show. So, if you had unlimited time and resources, which problem would you try to solve? Maybe let's start with David.
That's a very good question. So actually, because I recently saw some groups celebrating that they got access to supercomputers, superclusters. I was actually thinking to myself, well, we actually don't need that. So they wanted to also do something Bayesian. I thought, well, we can do that now without the supercluster from Germany. But I mean, with unlimited time and resources, I think what would definitely improve our understanding would be to actually, hard with sledgehammer style brute force extract the loss landscapes from neural networks, so that you exactly get the whole loss landscape of a neural network, and then we would have an understanding what is going on there. Same for the learning dynamics. So then because this is something that people now try to get their grip on, to understand how is it possible that gradient descent, stochastic gradient descent approaches work so well. And then if you would have infinitely many resources and time, then unlimited time, then you could do that and understand it. But of course, the more relevant thing for our world would be to do something towards, can we turn the current trends, be it AGI or not in the end, can we turn that into something for humanity and not against humanity? I think this is the more broader answer.
Mm-hmm. Jakob, what about you?
Okay, if it was purely driven by curiosity, not by ethic concerns, I think I would like to understand life, how it forms, what it means, and where it is. Actually, my main science goal is characterize Earth-like planets. So this is a small step in that direction. But yeah, I'm really curious about, are we alone, and what other forms are there?
Yeah, I understand that. Who would not be? Love it. Love that answer. That's great. And Emanuel, what about you?
Wow, really hard to add something to those two good answers. Again, certainly there would be more influential and more important problems, but I'm far from the right person to sketch a roadmap in these domains. So I will just say flexible yet affordable, somewhat generalized, maybe universal probabilistic modeling at all scales. Because I actually truly believe that calibrated probabilities can lead to truly transparent and trustworthy systems. And this doesn't really necessarily require a Bayesian twist. I'm not sure how this would turn out, right? But since I started to work with probabilities, and distributions, it almost always gave me a feel of like I'm on the right track. compared to like a little bit more limited knowledge from just looking at one point, like the broader perspective of that actually there's no certainty, and that also kind of is reflected in our everyday life everywhere, and to actually really grasp that in some sense is quite inspirational, I think.
Yeah, definitely. um, yeah, love that answer. For the interest of time, I will not comment. But second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be? David, let's start with you again.
Yeah, a great question. Also difficult question. So the I think so. Maybe something that well, I'm very lucky to have is that we have this Bayesian deep learning consortium. Like this is like a lot of people that do Bayesian deep learning. They write a book together. So there will be, I think maybe next year coming out like a huge book on Bayesian deep learning, co-authored by hundreds of authors. So I could probably have dinner with them already, with all these great minds. But if there would be one thing that is, if you say fictional, then maybe someone from the future that knows what will happen in a couple of years, and then talk to them. That would be, I think, quite enlightening. Obviously, yeah.
Yeah, I love that. Let me know when that dinner happens. I definitely need to come in with some mics. It sounds like there will be some very interesting conversation there. Emanuel, what about you?
Yeah, pretty difficult. I mean, to be honest, maybe someone who's alive right now. Maybe it will happen at some point. Let's put it out. Shout out to Pavel Ismailov. I probably pronounced the name wrongly, but I just started out with Bayesian neural networks when I came to David's group, and I read a lot of his papers, and I really appreciated them. They were really good, and I feel like that he has also I would be interested in some of his takes, because we've looked at very similar problems, and also had, I think, would agree on many things, maybe on some things not, and I would be interested in that. But maybe just more generally, I'm actually quite fascinated by Newton himself, due to his very broad influence on science in general. But yeah.
Yeah, that sounds about right. And the good thing is that he spoke English, even though maybe harder English than today's. So I'm curious how you would communicate, actually. And well, Jakob, let's finish with you.
Okay, given that David went into the future and Emanuel stays in the present, I will go in the past. I think I would like to speak with von Neumann. He's a character from the history, supposedly very smart, and I heard he was fun to be around. So I think it would be an enjoyable dinner. I don't think I would learn that much. He would probably be way too smart for me, but should be fun.
Yeah, I love that. I don't remember, but I think you're the first one to answer von Neumann. So amazing. That'd be weird if you were the first one, though, because I've been doing that for 6 years. Weird that he didn't come up yet, but maybe there are some listeners. Rafael, if you know, if you know, you know better than me probably. So let me know. Fantastic. Well, guys, thank you so much for taking the time. That was a great show. I really enjoyed it. Thank you so much also for the work you do. I think it's extremely important, not only because it's gonna unlock a lot of issues practitioners are currently having, but also I think it's helping a lot to make Bayesian inference still relevant in today's age, and I can only thank you for that, because obviously we all love Bayesian stats here, and we think they have something to contribute. But we always need to make sure they keep at the frontier, they stay at the frontier, because otherwise we're gonna lag behind. So thank you for being our knights in in binary armor at the frontier of Bayesian stats. And again, thank you so much for taking the time and being on this show.
Thank you for having us.
Thanks.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Loss and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.